Good afternoon, class. We are looking at exam 4 review, chapter 4 application of differentiation, and chapter 5 integrals, 6.1 area between the curves, and we're going to look at 4.9 antiderivatives, 5.1 area and distances. So we need to be very comfortable with differentiation so we can go with the reverse process. For example, the derivative of kx is k, where k is a number, is a constant. So therefore, the integral of k dx must be kx. However, any constant, the derivative is 0, therefore it must be kx plus a constant. K is a constant, c is a constant. Okay, everybody? So both of them are constant. Everybody should remember that. The derivative of x to the power of n is n x to the power of n minus 1. Now, the power rule is the reverse process. So the integral of x to the power of n dx is x to the power of n plus 1. So this takes away 1 from the exponent. This adds 1. Okay, this multiplies by n. It's going to divide by n plus 1. And of course, n can't be negative 1. The process is this. The derivative of x to the power of n, multiply by n, subtract 1 from n. Integration is the reverse process. So the reverse process, and it's going to go from bottom to top now. We're going to go this way. By the way, this one now, at this point, c is a constant, okay? We already established k is a constant. So is this c. In any event, so the reverse process, first, instead of subtracting, we are going to add 1. Then instead of multiplying, we are going to divide. So first we add 1 to n, then we divide by it. That's what gives us that. In any event, a couple of differentiation formulas that we know, and we're going to go with the reverse process. The derivative of e to the power of x is e to the power of x. Then the integral of e to the power of x dx must be e to the power of x. And as always, we add a constant because the antiderivative introduces a family of functions. Okay. The derivative of natural log is 1 over x. So the integral of 1 over x must be natural log and a constant. The derivative of sine is cosine, so the integral of cosine must be sine and a constant. The derivative of cosine is negative sine. So the integral of negative sine must be cosine. That means the integral of sine must be negative cosine and a constant. So this gives us this. And again, this constant is a number. And the derivative of any number is 0. So this is the reverse process. Same thing for tangent, cotangent, and so forth. If the derivative of tangent is secant squared, the integral of secant squared must be tan x plus a constant. If the derivative of cotangent is minus cosecant squared, then the integral of cosecant squared must be minus cotangent x and a constant. The derivative of secant is secant x tan x. So the integral must be the reverse process. The integral of secant x tan x must be secant x and a constant. And if the derivative of cosecant is negative cosecant cotangent, then the integral of cosecant cotangent must be negative cosecant x and a constant. Okay. Constant multiple, if you have a k, which is a constant multiple, you can put it inside or outside the integral sign. Makes no difference. It's the same thing, everybody. Inside or out has no bearing. That's the effect of a constant. Sum and difference rules, we had that for differentiation. We said, okay, differentiate term by term. Now integrate term by term. So if I want to integrate this one, I can separate them, integrate this one, and then this one, add them, subtract them, you name it. If the derivative of e to the power of kx is itself times k, the integral of e to the power of kx must be itself divided by k and a constant. So think about it. The derivative of e to the power of kx is itself times k. Now we are going to divide by k. And don't forget the constant. That's extremely important, everybody, to uh, understand what happens here. Very straightforward. So these are basic integration formulas, the reverse process of differentiation. So find all functions g such that g prime is 4 sine x plus 2x to the power of 5 minus square root of x over x. Here's the technique. Solution. Sometimes you will need to simplify first. Factor, cancel, remove radical notations, etc. Sometimes you will need to integrate using substitution, which is coming up. And again, reminding you of some of the formulas we wrote though. So the very first thing, even if we wanted to differentiate, we would do the same thing. We would separate this into two fractions, right? This, this one, this one. And we are going to use the exponential rule, and we say this is 2x to the power of 4. This one we're going to write as x to the power of 1/2. 1/2 minus 1. Remember when this one it has exponent 1. So minus x to the power of 1/2 minus 1 or negative 1/2. Now it's ready to be different, differentiated or integrated for that matter. So we are going to integrate this, and you need a dx, by the way. That is a dummy variable which indicates what is the independent variable, which happened to be x. So 4 sine x, you know the derivative of sine is cosine, the integral is negative, so minus 4 cosine x. So remember this. 2x to the power of 4, you add 1 to 4 and you divide by it. So 2 divided by 5, x to the power of 5. Again, just to show you in case we are looking at this, everybody. And for this one, let me just write it here. I would write 2 divided by 4 plus 1 x to the power of 4 plus 1. Okay, so I get 2 over 5 x to the power of 5. Now, the next one I will show you, again, it's going to follow the power rule. So minus 1 over negative 1/2 plus 1 x to the power of negative 1/2 plus 1 and a constant. So take a look at this. 1 over the exponent plus 1, x to the power of exponent plus 1. And we are going to simplify. As you know, negative 1/2 plus 1 is positive 1/2. And so this is minus 2. And x to the power of 1/2 is square root of x. And that's the final answer. Minus 4 cosine x plus 2 over 5 x to the power of 5 minus 2 square root of x plus c. Very straightforward, everybody. Each and every one of the terms here are going to use the power rule. This one. 2 over 5 x to the power of 5. Actually, we had that in the previous. This one, add 1, we get 4. 3 over 4, x to the power of 4. This one, add 1, you get 3 minus 7 thirds x cubed. Now, it's important to understand this means x to the power of 1. And so if we add 1, we get 2. So 1 over 2x squared minus 5x minus 5x and a constant. And we're done. It's that simple, everybody. What about x minus 5 squared? We should square it first, and you know a minus b quantity squared is as a squared minus 2ab plus b squared. So x squared minus 10x plus 25. Again, a quick reminder, a minus b squared is a squared minus 2ab plus b squared. And now, one by one, this is just add 1, you get 3, 1/3 x cubed. This one, add 1, you get 2 minus 10 halves minus 5x squared. This one gives you 25x and a constant. And you're done. Now, if you recall, for differentiation, we would also first cut it into 3 fractions. The same thing is going to happen with integration. So cut it into 3 fractions. This one, this one, this one. So this is 1. This is minus 7 over x. This is plus 2 over x. Now, to get to the rest of it, first we want to make sure we understand, okay, this is its x. This is, just so we can see, you don't have to write it, but this is minus 7 times 1 over x, and this is 2 x to the power minus 2. So why are we writing it in this format? Okay, because we want to do 1 by 1. 1 is simply x minus 7 times 1 over x. Remember, 1 over x gives you natural log. By the way, 1 over x or x to the power of minus 1, okay? And the reason we use an absolute value because of the domain of natural log from 0 to infinity. So minus 7, 1 over x gives us minus 7 ln of absolute value of x. And now this one, I want to show you this one using the power rule. So we are going to use the power rule on this guy. That means 2 over minus 2 plus 1, x to the power minus 2 plus 1. And of course, we're going to add a constant. So this is negative 2 x to the power minus 1. So it's minus 2 over x. And of course, a constant. The integral of 1 plus cosine t dt, first and foremost, make sure you see that t is the independent variable, meaning that the integral of 1 is not x, it's t. Okay. Cosine, the derivative is negative sign, the integral is positive sign, and a constant. Cube root of x minus sine x dx, and to do the integration or differentiation, we will change this to x to the power 1/3, right? You're going to use the power rule on this guy. So 1 over 1/3 plus 1, x to the power of 1/3 plus 1. Sine, the derivative is cosine. The integral is negative cosine. So minus negative cosine and a constant. Of course, we know this becomes positive, but I wanted to show you that it is sine that results in negative. And now 1/3 and 1 is 4/3. The reciprocal 1 over 4/3, that means reciprocal 3/4. And this is x to the power of 4/3, which is cube root of x to the power 4. I'm assuming nobody has any problem with the algebra. So going from here to here, there should be no problem. This is one fraction. This is another one. And we're going to change square root of x to the power of 1/2. So we have two fractions, everybody, this one and this one. So the first one, no exponent means exponent 1. 1 minus 1/2 is negative 1. 1 minus 1/2 is positive 1/2. And the second one is x to the power of negative 1/2. So this is just writing it, okay, properly. Now we are going to use the power rule for integration. So 1 over n plus 1, x to the power of n plus 1. So 1 over 1/2, 1 over 1/2 plus 1 over 1/2 plus 1 over 1/2 plus 1, x to the power of 1/2 plus 1. This one, 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1, and a constant. We just add one constant at the end. Done. This is it. This is the only calculus step, everybody. Everything else that we have done is algebra, and what we do from here on is algebra too. So as you know, 1/2 and 1 is 3/2. 1 over 3/2 means 2/3. 1 over 1/2 means 2. And the final answer is 2. You can say 2/3 x to the power of 3/2 or 2x to the power of 3/2 over 3 plus 2x to the power of 1/2 plus a constant. Of course, you can change this to square root of x or keep it. Either way is fine. It's not that big of a deal, this one. Well, this results in two fractions. This one is 1, and this one. And to finish the job, we are going to change this to 2x to the power minus 2, and 1 results in x. But what happens to this one, let me quickly show you. I want to integrate this one. I get 2 over minus 2 plus 1, x to the power of minus 2 plus 1. And I hope you see that as minus 2 x to the power of minus 1 or minus 2 over x. We should be comfortable with the algebra behind this, and I had shown this to you before in the previous page anyways. Now secant squared. The derivative of tangent, class, the derivative of tangent is secant squared. That makes the integral of secant squared tan x and a constant. And looking at this. Solve the initial value problem. dp dt, that means p prime of t is 2e to the power of 3t, and p of 0 equals 1. So the question is, what do we mean by initial value problem? Any equation containing a derivative is called a differential equation, or short DE. A function which satisfies the equation is called a solution to the differential equation. An initial value problem is a differential equation along with a specified value of the unknown function called initial condition. In other words, you have, in addition to the question to solve, you have a pair, and its duty is to help you find the constant, because remember, when you integrate, you get a family of functions. So what we are going to do, we are going to ignore this for now. If this class without this is just the basic integration, which means I'm going to put the dt on the other side, and the integral means I'm looking for p of t. Okay, you need this dt. So I'm going to ignore the pair. And this one we know how to integrate. Remember, e to the power of 3t. The derivative you multiply by 3, the integral you divide by 3. So you get 2/3 e to the power of 3t plus a constant. I'm looking at this one, class. When it's e to the power of kx, differentiation you multiply by k, integration you divide by k. Now, let's say this wasn't there. We are done. That's the good old integration anti-differentiation problem. What makes this an initial value, we have one pair, 0, 1, meaning replace the t with 0 and p of t, or y, if you will, with 1. So p of 0, 2/3 e to the power of 3 times 0 plus c must be equal to 1. And the essence of this is that you have found a way to get to the constant. What is this? A family of function. What will this do for you? You find the missing c. As you can see, it's e to the power of e to the power of 0, which is 1. 2/3 plus what number is 1? 1/3. So what is, therefore, p of t? 2/3 e to the power of 3t plus 1/3. So what is this? General solution. This helped us find one solution, particular solution, it's called. Okay, that's the idea. Another example of an initial value problem, and we are going to ignore the fact that we are given a pair, 1, 4. Ignore it. Just do the math. This needs dx so we can integrate. So y is the integral of 1 over x plus 1 over square root of x dx. And we know how to handle this by rewriting 1 over square root of x. This is x to the power 1/2, comes up, becomes negative. And this, we know it's not natural log, right? This one is the natural log. What about this one? I hope you remember. We've done this before. 1 over negative 1/2 plus 1, x to the power of negative 1/2 plus 1, and we have a constant. And so negative 1/2 plus 1 is positive 1/2. This reciprocal becomes 2 square root of x plus a constant. So again, if we didn't have the pair 1, 5, we would be done, because we just found the general solution, everybody. This is the general solution. And why is this called the general solution? Because of this, it's a family of functions. It's infinitely many different functions that shifts up and down based on the value of c. Now we're going to replace the x with 1 and y with 5. As you know, ln1 is 0. and this is 2 times 1 is 2. 2 plus what number? Gives you 5 is number 3. Replace it, and now you have a particular solution. So in essence, what the initial value does, it gives you a pair, that's all. And that pair can help you find the constant. So not a big deal. Very simple, everybody, okay? Example 14, rectilinear motion. A particle moves in a straight line and has acceleration given by a of t equals 60 plus 4. Its initial velocity v of 0 is minus 6. Sometimes they call it v of 0. V equals v sub 0. Minus 6 centimeters per second, and its initial displacement s of 0 is 9 centimeters. Find its position function s of t. So what is a rectilinear motion? Rectilinear motion. For motion in a straight line with constant acceleration, acceleration is constant. Initial velocity of v sub 0 and initial displacement s sub 0. The displacement after time t is s of t equals half of at squared plus v0 t plus s sub 0. So rectilinear motion says acceleration is fixed. Okay. But this one actually a of t is 60 plus 4. So it's not fixed. It's not a constant. This is really, in essence, uh, not a rectilinear motion. But in any event, uh, by definition, acceleration is the derivative of the velocity function. Velocity is the derivative of the position function s of t. And therefore, in this case, what is given is v prime of t equals a of t. That's given. So if I want a v of a t, I'm going to integrate this antiderivative. This gives you 6 over 2 t squared. This is 3t squared. This is 4t and a constant. I hope everybody can see what we are doing just in case. So v of t is the integral of 60 plus 4 dt, and we get this one. Now, we don't have a constant. This makes it an initial value problem, and v of 0 equals negative 6, so replace it. V of 0 is c, v of 0 equals minus 6. In other words, if I replace it, class, v of 0 is what? 0 plus 0 plus c, and it's minus 6, right? So that means c must be minus 6. And that means here's v of t, 3t squared plus 4t minus 6. That's the meaning of it. So very straightforward, everybody. What is s of t? Let's integrate this. So if I want to integrate this, I hope you realize 3 divided by 3 is 1. So this is t cubed. This is 2t squared. This is minus 60. And I'm not going to write plus a c, but rather plus a d, because I don't want you to think these two are the same. Plus some other constant. That's the idea. And let's just write it in case so you can see what I'm referring to. So we are using the integral of 3t squared plus 4t minus 6 et. That's what we're doing, okay? And now we are going to use this. So if S of 0 is 9, S of 0, as you can see, is 0 plus D. And it's 9, then D becomes 9. And you replace it, and you have S of t, which is t cubed with the plus 2t squared minus 6t, and a D that you found it to be 9. And now you've done very straightforward, everybody. The purpose of this question was to remind you, you take the derivative S, the derivative gives you V. V, the derivative gives you A. And reverse process brings you back to S of t, which is anti-differentiation, integration, you name it. A sample of cesium-137 with an initial mass of 79 milligrams decays T years later at this rate. Rate means the derivative function, okay? Minus 1.8249 e to the power of negative 0.0231 t milligrams per year. Find the mass of the sample after 23 years, and then they want us to go with 1 decimal. Remember, when they want you to round, you do the rounding at the end, not any of the intermediate steps. So what is given, this is the rate. So if you call the function itself m of a t, so if you let m of t represent the mass of cesium-137 after t years, it's a radioactive substance, then what this is dm dt. So this is dm dt, and this is the initial value m of 0. So we're going to go through the process to find m of t, and then m of 23. So that is the step. Number 1, this is the MDT. Number 2, the initial value m of 0 is 79. We use the formula to find m of t and then m of 23. So what is m of t? If you put this here, dt, and integrated, it becomes m of t. So I hope you recognize m of t is this thing times dt. Okay, everybody? Now, again, remember how you differentiate e to the power of kx, you multiply by k. How do you integrate? Divide by k. So the answer is itself, divide by negative 0.022231, and you have a constant. So we have this number, negative 1.8249, divided by the coefficient of t, then e to the power of the same thing, and a constant. So when you put this into a calculator, believe it or not, it gives you 79. So 79 e to the power of minus 0.0231 t plus a constant. We need to find a constant. We need 1 point, and 1 point is given when t is 0, m is 79. So replace this with 79 and t with 0. Well, obviously, if the power of 0 is 1, 79 is 79 plus c, so c must be 0, and that's your function. Now what? Plug in 23, put it into a calculator, write it with a bunch of decimals. Then we want 1 decimal. 4 next to this 3 doesn't change. So 46.4. What are the units? Milligrams. So pretty straightforward. All right, areas and distances. The method of exhaustion, areas of familiar polygons, such as triangles and rectangles, enable us to find the area of more complicated regions by filling the region with increasingly smaller elements of known area. This is called the method of exhaustion. What do we mean by that? Let's say in the olden days when they didn't know the area of a circle, what did they do? Well, if you inscribe a triangle, you can calculate the area of a triangle. That's an approximation. If you add to the number of sides, make it a square and so forth, that has the area closer to the actual area. This one has area pentagon, has a even closer area. As you add to the number of sides, you get a better approximation. That's the idea behind this. Okay, everybody? So this is called the method of exhaustion. Before they knew the area of a circle was pi r squared. What else they did? They also put that circle into a, this was the easiest way, and they would average it. They could put it into a four-sided figure, five-sided figure, and then average out the two. Now, what about the area under a curve where we don't have a specific geometric shape? Same process. The area problem. Find the area of the region S that lies under the curve y equals f of x from A to B. This means that S is bounded by the graph of a continuous function f, where f of x is greater than or equal to 0 is above the x-axis. The vertical lines x equals A, x equals B, and the x-axis for y equals 0. Therefore, you're looking at this. S is x comma y such that x is between A and B, y is between the x-axis 0 and the function f of x. That describes this area. So how do you find it? Well, you put some, you cut it into rectangular pieces, everybody. For example, if we do this, we cut it into, using 3 lines, we cut it into 4 rectangles, okay? Then here's what happens. I can use any side. For example, if I use this ends, the left end points, this would be the area for the first one. This is for the second one. This is for the third one. This is for the fourth one. Meaning, I know this width is fixed. So B minus A divided by however many ends. In this case, I cut them into 4 equal regions. That would be the width. And by the way, the width, they can be different, but it's easier if they're identical. The height, if I use the left end points for each case, those are the case. If I use the right end points, this would be the height for the first one, for the second one, for the third one, for the fourth one, or I can use any other point in between. Normally they use the midpoint, makes no difference. It's an approximation. So what are we saying here? We are saying it gives you an approximation. But what do you think happens if we cut it into more subintervals? Then the approximation becomes better. Now, this is called the Riemann sum, the summation of I going from 1 to n of f of x of I delta x. Delta x is this width, b minus a, divided by n. What is n? However many subintervals. We cut it into 1, 2, 3, 4. N would be 4 here. So if you look at just one of them, so I want you to see how that formula plays out. If you look at this one, get the first one, just the first one. The width is delta x. Here's the height, which comes from the function. Evaluated at some point, this point or anywhere in between. That's what f of x of I is. So f of x of I times delta x, and it's the summation of those. F of x of 1 times delta x all the way to f of x of n times delta x. That's how you arrive at the answer, everybody. So very straightforward. And we are ready to move on. So that's the concept. Now, suppose a continuous function f is defined on the interval of a to b, closed interval. If the interval is divided into n subintervals so that delta x is b minus a over n, x sub 0 is a, x sub 1 is a plus delta x sub 2 is a plus 2 delta x sub n is a plus n delta x equals b, then a Riemann sum associated with f is the sum that was mentioned in the previous page. X sub I is any point in the interval of a sub I minus 1 to a sub I. So that's pretty straightforward. Geometry and a procedure called Riemann sum. Number one, partition the interval of a to b into a few, say 4 subintervals. That's an example. Make 4 rectangles. The width becomes delta x equals b minus a divided by 4. And the heights are f of x sub 1, f of x sub 2, f of x sub 3, f of x sub 4. Make 8 or more rectangles. As the number of rectangles increase, the approximation gets better. And that's the key. So we have left endpoints, right endpoints, midpoints. You don't have to memorize any of them. I'll give you the concept, and then I'll show you how easily you can remember it by looking at this concept of A to B and cutting it into n pieces. So delta x, b minus a over n. So what is this one? If we go from A to B, x sub 0 corresponds to A, and x sub n for this one corresponds to B. For the left endpoints, we use all the left endpoints, so B is not used. For the right endpoints, A is not used. And for the midpoint, you pick the point between these two. That's why it's called x1 bar and so forth. And I will show you with a couple of simple examples. Therefore, the area is approximated with this Riemann sum, okay? F of x of 1 times delta x all the way to f of x of 4 times delta x. The area under the curve is exactly equal to the same thing if you take the limit and we let n go to infinity. So the summation I going from 1 to n of f of x of I delta x, this limit is identical to the area by definition. So delta x is b minus a over I over n, and x sub I is a plus I delta x. What do we mean by this? Let's look at a very simple example to make some sense out of this. Use the left LEP, left endpoints, REP, right endpoints, and midpoints rule with n equals 5 to approximate this integral. The integral of 1 to 2, 1 over x dx. That gives rise to an area under the curve if we are talking about a positive function. Okay, it could give us the signed area, okay, different subareas. However, the concept is very simple, first and foremost. I'm reminding you about the Riemann sum and the left endpoints, the right endpoints, the midpoints. And you don't have to memorize any of those formulas. I'll show you how to find it nice and easy. Number one, understand what's your function. F of x is 1 over x. That's the first thing that you need to realize. And we're going to go from 1 to 2. So A is 1, B is 2. So that's understanding what you want to do. Again, what is the function? Whatever is in there without the dx. The integral. What are your limits A and B? Lower limit is A, upper limit is B, from 1 to 2. Now we're going to go to 1. Delta x is B minus A over n. 2 minus 1 over, and n is given as 5. Okay. So let's graph this function. You remember y equals 1 over x, and we want to go from 1 to 2, and we are going to cut this into 5 equal subintervals. Okay. And we want this area, everybody. And we're going to find this area by an approximation of 5 rectangles. So delta x is b minus a over n, or 1 over 5, right? 2 minus 1 plus, obviously, 2 minus 1, 1 over 5, or 0.2. So pretty straightforward. All right. All right. The next step is I want to use the left endpoints, the right endpoints, the midpoints. How do I do that? Very simple. We are going to make this larger so it becomes clear from 1 to 2. And we're going to cut this into 5 equal parts. So A is 1, B is 2, and we are going to add 0.2. So we get 1.2, 1.4, 1.6, 1.8, and 2. So 1 to 2, we made it large so it becomes easy to see. So we are making this interval of 1 to 2 large, huge. And then we are adding, from the beginning, we are adding 0.2. Now this is A, this is B. Now for the left end points, we are going to use all the left points. We are going to use this one, this one, this one, this one, this one. We are not going to use B, so ignore B. For left end points, we are not using that. So this formula, f of x of 1 delta x, just think about this one. So 1 over 5, so this delta x is 1 over 5. The first one, 1 over 1, because the function is 1 over x. 1 over 1, 1 over 1.2, 1 over 1.4, 1 over 1.6, 1 over 1.8, but we're not going to put 1 over 2 there. Now, at this point, you put it into a calculator with many, many decimals. And that's your answer. So that's for L5. Why 5? L5, because n is 5. Okay, everybody? Now we want to go with R. We are going to use the same formula. Now I'm going to erase my work. Take a look. And I'm going to say for the right endpoints, everybody, I'm not going to use this one. I want to use the right endpoints, right? So same thing, 1 over 5, 1 over 1.2, 1.4, 1.6, 1.8, all the way to 2. And if I put to a calculator, I get this answer. Also notice the following. This part is the same as this part. So when you do the calculation, keep track of that so it makes it easier. Okay. What about the midpoint? Again, here's the easy part for the midpoint, everybody. I'm going to erase my work. Here's the midpoint. So I'm going to use this point clearly is 1.1, right? What would be this one? Add 0.2 or just 1.2 plus 1.4 divided by 2 is 1.3, 1.5, 1.7, 1.9. So I hope you see this line segment really helps. So M sub 5, we use this one. How about that? Very straightforward. One over 1.1, 1.3, all the way to 1.9, put it into a calculator. And by the way, that is normally a better approximation, everybody. So that's a very straightforward concept. The velocity of a moving object is given by the function v of x equals 3x, where x is in hours and v is in miles per hour. Use geometry to find the area under the graph, which is the distance the object has traveled during the first 3 hours. So you draw v of x equals 3x. This is time in hours, and this is the velocity. So this point has coordinates 3 times 3, 9. The area is 1/2 base times the height. So the base is 3, the height is 9. So 1/2 times 3 times 9, which is 27, divided by 2. So the distance is 13.5 miles. What about between third and fifth hour? Looking like that. You have several choices. One is to calculate the entire area and then subtract this one from it, right? Meaning half of base times the height. The base is 5, and then 3 times 5 is 15. Subtract this amount, you already have it. Or just recognize this one as a trapezoid. And the base, the small one is this one, the large one is this one, the height is this one. So area is 1/2 the height times b1 plus b2. So the height is 5 to 3, this distance of 2, okay? And the base, this one is 9, right? And this one is 5 times 3, 15. So this one is 5, 3 times 5, 15. And these two cancel each other, and we get 24 miles, okay? So that's pretty straightforward, I would say. Use the definition to find an expression for the area under the curve f as a limit. Do not evaluate the limit. F of x is x squared plus the square root of 1 plus 2x. X is between 4 and 7, x inclusively. Find delta x and x sub I. Well, a is 4, b is 7, delta x is b minus a over n, 7 minus 4 over n, which makes it 3 over n. X sub I is a plus I delta x. It's 4 plus this expression, which is delta x times I. So 4 plus 3i over n. So the area under the curve, according to Riemann sum, is this limit. The limit of r sub n as n approaches to infinity, or L sub n as n approaches to infinity. This is r sub n. So summation of f of x sub I delta x as I goes from 1 to n, take the limit. If you take a limit and let n go to infinity, it becomes the actual area under the curve. So what do? We replace into the function x sub I, and x sub I is 4 plus 3i over n. So the function is this, and x sub I, we found it to be 4 plus 3i over n. So if I plug in, this becomes a 4 plus 3i over n squared plus the square root of 1 plus 2 times the same thing, 4 plus 3i over n. So that means f of x sub I is this expression. So I'm going to replace this with this expression here, and I'm going to replace the delta x with 3 over n. So into here, f of x sub I is this parentheses, delta x is 3 over n. We will discuss that later on, how to evaluate this limit. But for now, this represents the actual area under the curve. The limit of the summation I going from 1 to n of 4 plus 3i over n quantity squared plus the square root of 1 plus 2 times 4 plus 3i over n, the whole thing times 3 over n. Determine a region whose area is equal to this limit. Do not evaluate the limit. The limit as I goes from 1 to n of 3 over n square root of 1 plus 3 over n as n goes to infinity. So we just write the expression. A is the limit of this expression, or R sub n. R sub n, the right endpoints. N is the number of subintervals. The limit as n goes to infinity of summation of f of x sub I delta x as I goes from 1 to n. So we are going to put this next to each other and compare and contrast to see what's going on, everybody. Clearly, a 3 over n is this delta x, and this expression is f of x sub I. So 3 over n is delta x. F of x sub I is 1 plus 3I over n. So what is delta x? B minus a over n. What is x sub I? A plus I delta x. So let's write this too. We know this one is 3 over n. And we know this one should be what's underneath here, 1 plus I times 3 over n. We're going to rewrite this. So this is 3 over n. We're going to rewrite this as 1 plus I times 3 over n. So we can see that it's a plus I delta x. So if it's a plus I delta x, a must be 1, b minus a must be 3. So b minus a is 3, a must be 1, right? According to this, b minus a must be 3, and according to this, a must be 1. So b minus 1 is 3, so b becomes 4. So what we are looking at, the function y equals f of x is a square root of x on the interval of 1 to 4. And that is not unique, everybody. So this is the uh, operation that is taking place, the operation of square root, if you will. However, we could do the following. So take a look. So this is not unique because of the reason. Delta x is 3 over n. You can't change that. But what if we write x sub I is 0 plus I delta x, which makes it 3I over n. And in that case, a becomes 0, b becomes 3. So according to this, we decided that a is 1. But if a by any chance be 0, then b becomes 3. And how do you make this happen? Then y or f of x is the square root of 1 plus x on the interval of 0 to 3. So this is the reverse process. You can work on this and expand it to get to this one. You can work on this and expand it to get to this one. The point being, you could represent them in 2 different ways. But if you decide that a is 0, this can't be x just like that. So you can't do that for this one. Rather, 1 plus x. So you take this one as x sub I, if you will. You can think of this as x sub I, 1 plus x sub I, and that will take care of the business in that. If you take the whole thing, see, in this case, I want to make sure you understand. In this case, this whole thing is x sub I. In this case, this will work as x sub I, okay? In any event. And again, we have this Riemann sum. The velocity graph of a car accelerating from rest to a speed of 120 kilometers per hour over a period of 30 seconds, 0 to 30 seconds, is shown. Estimate the distance traveled during this period. Use m sub 6, the midpoint. To get the most precise estimate, round your answer to 2 decimals. Please understand what we are trying to say here. The area under the curve of a velocity function represents the distance. You want the total area to represent the total distance covered from 2. In this case, the 30 seconds from 0 to 30 seconds. That's the idea. We can use the left endpoints, the right endpoints, but they have specifically asked for the midpoint. So this is the exact area under the curve. They want us to approximate it by cutting it into n6 equal parts, which means delta x is b minus a over n. And since this is t, we are going to call it delta t. Remember, x is a variable, is the independent variable, is a dummy variable, but more specifically here is t. So delta t is b minus a divided by n, and n is 6. So 30 minus 0 over 6, 5 seconds. So intervals of 5 seconds, everybody. So this is 5, 15, 25. So you cut that into 6 equal intervals. And remember, because this is kilometers per hour, we want to recognize 1 hour is 3,600 seconds, 60 times 60, right? 1 hour, 60 minutes, 1 minute, 60 seconds. So delta t is 5 seconds. How many hours is that? Divided by 3,600. So delta t is 1 over 720 hours. Okay, the units of seconds changes to the units of hours. Why are we using that? Because the speed is given as kilometers per hour. Or you can keep this unchanged, don't change that, then change this to meters per second. Okay, that's not what we want to do. All right, so having said that, this interval of 0 to 30, we cut it into 6 equal parts. 0 to 30, that's 5, 10, 15, 20, 25, 30. We cut it into 6 equal parts, and we want the midpoint. Midpoint has this formula. I'm not going to, worry about the formula so much. Delta x times f of x of 1 bar, f of x of 2 bar, add them up all the way to the end. So how do we get that? And that's what's it's important for me to see, that you are going to go with the midpoints. So right here is the midpoint, 2.5, 7.5, and so forth. So that's the midpoint between these two. Okay. And that's the midpoint between these two, 5 and 10, and the next one, the next one, and the next one. And the height of the function at that point. These are the lines. So the idea is that to find this area, everybody, then add this one, the next one, this one, the next one, and the last one. That's the idea. And again, in between, so everybody can see, in between here is 2.5, then 7.5, keep on adding 5. 12.5, 17.5, 22.5, 27.5. So these midpoints, here is 2.5. Here's 7.5 and the rest of them, okay? That's what I mean. This line segment is really helpful. So 1 over 720, that's your delta t, or delta x, in this case, delta t, and v of 2.5, which means you have to guesstimate that from the graph. Okay, so you don't have to worry about it too much for the exam. It's very easy to read that. But the idea is that just from here, you read this height, okay? Look at this one. You read this height because you want the uh, functional value at this point. And this seems, if this is 40, this is 80, it seems to be 31.25. This one, remember, this is 60. So this is maybe about 66. This is 80. Okay. That means this is 100. This is almost halfway close to 90, and so forth. These numbers, class, it's all a matter of reading those points. You see those points? They're y coordinates, if you would, which is velocity coordinates. You don't have to worry about that too much, but I want you to see how we arrive at it. You put it into a calculator, and you end up with 0.725 kilometers.